Hi, everybody. I took a look at that last week's video and of class and saw that a couple of the examples, the screen wasn't on there. So that's my fault. I apologize for that. Just my lack of experiencing in navigating with Zoom. But anyway, I wanted to redo a couple of those examples and get them posted up for you so that you have those to go by. And then I will do the same with this class on Thursday. But in the meantime, here's a couple of examples that we did the other day in class. Now, I did go ahead and did do or taught a lot of the background to this again, and just to review that real quick. What we did was we started off with a simulation of somebody shooting basketball, and this was kind of the scenario. This guy here had and the names don't get confused here. This is Shane. I usually change the names every year when I had different students in class, but anyway, he made 32 out of 50, which is 64% of the shot. And the idea was, well, if we wanted to know what his true average was, that would be the true percentage or proportion that he made, which was 80%. And that is, where does that come from? That comes from the problem. So we'll take a look at an example over here to link that. But so so what we do is we formulate these hypotheses. And again, I'm assuming you saw the videos of how to do that. And, again, I can take more questions on that in the future here. But, basically, because the scenario says we think he's full of baloney, that would imply that, he's not that good. He's less than that. And so so these would be the hypotheses. All right. And so the basic idea is, well, if this really was true, how likely was it that he got 64% or less, if that's his ability level? So looking at the other activity that we did in Staplet, we simulated that results. Now, the first time through here, I made 40, simulated 40 out of 50, which ironically was 80% on the nose. So we could do it again, and I quickly added 999 groups of 50 on there. And this was the distribution of them. Okay, so you can see that we had a bunch of them at 80 and so forth. But the key here is that if we counted up the number of times that he got 64 or less, and the computer did this for us, it was only 7 out of 1,000. That's 0.7%. I mean, that's less than 1% of the time. So if he was to go ahead and do that back here, that would be very unlikely to happen, but it did happen. So the only other explanation might be that this alternative is true. Okay. So we went ahead and actually, went through how to, calculate all this stuff down here with the Z-score and so forth. And I showed you some, different software that basically does what your computer does, or what your Excel spreadsheet does. But basically, what we do when we test these hypotheses is we don't do a simulation. We take a look at the sampling distribution. And I actually don't have real quick handy right here what the statistic is for that, but it is p hat. Oh, here it is, right over here. I do have it handy. It's p hat minus p over the square root of this. In other words, the sampling distribution is going to center on this p, and it's going to have this as a standard deviation. So when we standardize that, same probability that we can, statement we can make about, p hat being less than 64%, if the true proportion was 80%, we can answer using the Z statistic, and those probabilities would be identical. So essentially what we do is we plug in the 64% here, the 80 here, and 50 would go in here. So 0.64, 0.8 here, and then 50 here. and we would have gotten negative 2.83 approximately. And so if we use our standard normal density with the Z distribution, and again, you should have went over all this in the videos. What we find is that that probability of that occurring is about 0.2%, okay, which, you know, isn't exactly what we have back here, but it's, you would have to admit, it's pretty darn close, okay. So you know, actually, yeah, it would be 0.2%. So the idea is that that's pretty unlikely, okay. This would say, what, you know, 2 times in 1,000, or, you know, 23 times in 10,000 or whatever, but our simulation was, again, 7 out of 1,000. But you get the idea that this probability model mimics this, okay, without having to do the simulation. So essentially, we can get all this information based on this hypothesis that we developed from the scenario here. So that's kind of the background of it. So what I'm going to do is I am going to, you know, get into this ALEKS example here, and we'll go ahead. And again, you may have to stop the video here to get familiar with this, but I'm going to go through it real quick. But we're saying here that our hypothesized value is that 35% of the students will match their first time using this site, okay? And the writer for the paper wants to test this claim, okay? And we're going to go ahead and see if we could, you know, see or have some evidence to suggest, you know, is there any evidence to suggest that this isn't true, or in other words, it's not 35%. Now, if I'm looking here, and I guess maybe if I just read it, at nearby college, there's a school-sponsored website that matches people looking for roommates. According to their school's report, 35% will find a match their first time using the site. A writer for the school paper tests this claim by choosing a random sample of 170 students who visited the site looking for a roommate. One of the surveys said 66 of the students surveyed, 66 found their match for the first time. Okay, so, you know, essentially we got 66 out of 170. Now it says, complete the test below to see if there's enough evidence to reject the claim that the true proportion is 35%. Okay, so really here, the way this is worded, and this is kind of key here, you know, our null hypothesis is always going to be an equal statement. So, you know, I'm going to go ahead and put that in there, and P equals 0.35. Now, again, this is what we're testing. We have no way of knowing this absolutely 100% sure, right? But what we're going to do is, based on this sample here, see if we have evidence to reject this claim. Now, the scenario would have said something about it maybe being higher or lower. It doesn't say that. All it says is just says, see if there's enough evidence to reject this claim, okay? And so what I'm going to do here is I'm going to say that that alternative is, well, if we don't, you know, we're not saying, well, the effect might be greater than or less than. Specifically, we're going to use not equals to take both into account, okay? So sometimes you'll see the word differs, you know, and this implies that, you know, does the true percentage differ from 35? So I'm going to put in here the P and the 0.35, okay, and that would be for my hypotheses. Now, back here, again, in order for that sampling distribution, for this statistic to follow a normal, what you want to do is, you know, determine whether or not the conditions hold, okay? Because again, if you know, typically if we have too small of a sample here, that distribution of the Z statistic is not going to be normal, okay? It won't be a Z distribution, okay? So in order to use it, we have to make sure the conditions hold. So basically, they give us the criteria here, and they help you out that if you take the N times P, it has to be greater than 10, and also N times 1 minus P. So, you know, if I took 0.35 times 170, okay, because that is my my N is 170 and my P is 0.35. So I'll just use this calculator right here. Okay, and then there's no equal button here. You just have to hit the enter. So I got 59.3. Okay, so if 35% times 170 is going to be greater than 10, then both of those. Now, they do require, I guess you have to put the numbers in here. So, just, I guess maybe they're verifying that you check it. So we'll go ahead and put that in there. And then I'm going to take 0.65, right? That's 1 minus 0.35 times 170. Okay. And I'll put that number in there, which is 110.5. Okay. So we got that part down. The conditions hold. And now what we want to do is we want to find the value of our Z statistic. Okay. So we could, just go ahead and put those numbers in here. This is kind of where that template comes in. And I'm just going to have, because I'm going to be swapping back and forth here. I'm going to set this up in here. So if I can remember 66 out of 170, we should be good. So I am going to go to the template here, where I'm going to take a look at the proportion template. Okay. And what I'm going to do is we're doing a test for one proportion, Z test for one proportion. So I'm going to type in an equals here, and 66 divided by 170. Okay, so I could have done that on a calculator, rounded it, but this just is kind of a easy way of figuring out p hat. So we got 38% here. Okay, we put in our hypothesized value. That's our null hypothesis, which is 0.35, and we type in the 170 for the sample size here. And we do have a two-tailed test, and I think, if I remember right, they asked us to find or they gave us a 0.05 alpha level. So yeah, that goes in here. So here's the Z statistic. Here is the p-value for the left tail, the right tail. And in this case, we'll see here when we type our answer in the 0.295 for the two tail. Okay. So my p hat is going to be 0.388. Okay, and I think they want that to 3 decimal places, if I'm not mistaken. So yes, so this is a two-tailed test because of the not equals up here, and 0.388, provided my memory's right. Okay, and so there we have that. Okay, and what we want to do is shade the area represented by this. Okay, whoop. You know what? I put in my p hat. I should put in my Z statistic. It's 1.045. Sorry about that. 1.045. 045. Okay. So the p hat gives me that Z statistic. Sorry, I was typing in the p hat here. Okay. And so there we have that. And so what I want to do is shade this. So this is a two-tailed test. All I have to do is just hold this over here and it'll shade it. And so basically what we're saying is that area to the right and to the left of the positive and negative of the Z statistic is going to be equal to this p-value down here, which I don't know if I can, I can't scroll it off to go back over. Let's slide this over here. Oh, there we go. Okay, so what I'm going to do is I'm going to type out the 2.25 or 295. And I think they want that to 3 decimal places, 0.25. And since it's rounded to 3 decimal places, that should be a 6. Okay. All right. So so there we have our p-value. Okay. So I'm going to go ahead and just check this. Oh, I didn't answer something here. What B, C, oh, D. I'm sorry. I didn't scroll down here. Okay, so anyway, that's our p-value here. So if we come up with a conclusion, and again, that's all, part of that, those parts back there, I'll kind of go back and review that again. But here we have the conclusion. And so we want to pick the proper response. So ours is greater, right, than 0.05. I mean, we've got a pretty big p-value here, 0.29. So since our p-value, we're not going to choose these less than, is greater than the significance level, the null hypothesis is rejected. Well, that's incorrect, right? We only reject whenever the p-value is less than that. So we're going to have to go ahead and select this one and say the null hypothesis is not rejected. In other words, there's not enough evidence to reject that claim that 35% will match. Okay, so I'll go ahead and check this, and everything's good to go here. Okay. They got me here. Start your number with a decimal point. Okay, so maybe I should have put 0.035 there. But so if you kind of look at the big picture here, right, that, the larger z values, right, are going to be out here further to the right or further to the left, depending on if they're positive or negative, which would mean these areas would get smaller, which would make the likelihood of our p-value being smaller and the likelihood of rejecting it. So the idea is the bigger discrepancy that we have between what we hypothesize and what we actually got with our data, as that gets bigger and bigger and bigger, the z statistics can get bigger and bigger and bigger. And all this does is just basically account for the variation, okay, that goes on here. But the idea here is that we make a decision based on that data. So in other words, it's really not unlikely to get a sample proportion of 38.8% if this is true. Okay, that's not that unlikely. Okay, in either direction. Okay, so to go, almost 4% to the right or 4% to the left. So we'd have to have a bigger difference between those two values here in order to reject that claim. So that should kind of make sense in terms of our intuition. All right. So this is one with the p-value. Okay. And what I'm going to do is I am going to go back and jump into one here with a, see if I can find one here. Alex. Okay, so I think I came down here and pick one. Standard deviation. Don't mind me while I'm talking to myself here. Introduction hypothesis for proportion using the p-value, and I want to do one here with the critical value. Okay, so if I could find one here. Oh, here we go. Okay. So if I quickly go through this one here, again, I'm not going to go through all that stuff in the beginning. Again, here we have a scenario here. We're going to go ahead and write the hypothesis. And the only thing here, we're just not going to find the p-value. We're going to use this method here again to go ahead and calculate the critical value and compare our z value to it. So here we start off here with, again, this magazine TechWorks reporting that 88% of those software engineers say that, hey, this is a great place to work. As a veteran headhunter, you claim the percentage is not correct. Okay. So you go out and you survey 210 and 196 said that it was a great place to work. So again, what we're going to do is we're going to be asked to test that hypothesis and see if there's enough evidence to reject it now at a 10% level, okay, support our claim that, again, this is a great place to work is not 88%. So the phrase is not is going to tell us what our alternative is. So I'm going to put in this equal sign here again. So we're going to say P equals, so my P 0.88 And I come down here again, and that phrase is not, tells us that we're going to have not equals again. All right. So put my P in there and 0.88. And I better go back up here. 0.88. Okay. So again, we've got to go ahead and calculate those values here. And we have 210, right, for my n. So if I take 210 times 0.88, put the right number in there. Okay, so that turns out to be 184.8. And down here, if I take 0.2, which is 1 minus 0.88, and I multiply that by, again, the 210, I get 25. So 0.2. So we are well above the cutoff here of 10. Okay, we're definitely greater than or equal to that. Okay, so what we need to do now is we need to go ahead and calculate the critical values on this Z curve. Okay, so it's nice that they give us this picture here. And I should probably, well, I'll get into what this calculator, because you can use this, but I know that it's highly encouraged that you do use your master sheet. Okay. And so when we come in here, there's really no section to go ahead and find those critical values, or at least I could see. And I didn't make this up. So I don't know if it's in your critical. Yeah. Okay. So it would be for your normal calculator. Okay. So, if we go ahead and, use this calculator here, which I haven't used yet here. I'll tell you what, I'm going to go ahead and show you how to use this first. What we're going to go ahead and do is calculate the Z values at the point on here. And since the alpha is 10%, if I go back up here, if you remember that, 10% right there on top of the calculator, that means that I want 5% in each of these tails. Okay, so if I use this calculator right here, this Z, okay, and I type in the area that I want to the left of it, 0.05, okay, and hit enter, that's giving me 1.645 if I want 3 decimal places. Okay, so this is going to be a two-tail test. So we're going to enter these two values. So that would be the one on the right. So this is giving me the area to the right of 0.05 to the right. So I am going to type in 1.645. And due to symmetry, you don't have to do this again. I'll do it on the calculator, but it should be negative 1.645. Okay. So if I go ahead and clear this out and select this Z again, and so if I want 5% to the left, that would be 95% to the right. The area is half down up, and there's your negative 1.645. Okay. So now I need to find my test statistic. Okay. And that is going to be the Z value when I plug in all that stuff here. So that would probably be easiest if I go ahead to the proportion template. And if I just go ahead here and substitute in my P hat, which again was, remember here, close this out here, 196 out of 210. So I'm just going to put equals 196 divided by 210, just skip a little bit on the calculator. My hypothesized P value is 0.88. And we had 210. Substitute that in. This is a two-tail test. So, by the way, here's my p-value exactly. Okay, But what I'm looking for here is the Z statistic, which is 2.37. Okay. So, we got 93%, which is higher. Okay. So we would expect a positive Z statistic. So if I go back here, right, this value is higher than this. So we're going to get a positive value for our Z statistic. Okay. So what I'm going to do is I'm just going to type that Z statistic in here. So let me move this around here again. So my Z statistic is 2.37. And they want 3 decimal places. So this is one of the joys of using Alex. Type in one little decimal place wrong, but marks incorrect. So there we have it. Okay. Now, before I answer this last part here for the conclusion, you can definitely see that I'm beyond or in that zone here. So if I did compute the p-value, which we did over here, p-value is actually 0.0173. That would be the area to the right of this point over here, and also to the left of negative 0.3 or 2.378. Okay. So the idea is that, if that's my area, that's that probability of getting those results if the null is true, which is pretty darn small, right? It's only about a 2% chance, okay, or 1.7% chance. So that would give me evidence to reject the null. Here I have a definite, cutoff point, which is 10%, and that value is less than 10%. So again, if I was using the p-value method, I would just reject it. But this is kind of the old-fashioned way of doing this without knowing the p-value. So let's just pretend I didn't know the p-value. All I knew was my Z statistic, which is 2.37. Okay, that means that if I have a value that's beyond the 1.645 to the right, or beyond the negative 1.645 to the left, I don't know what my p-value is, but I know it's less than 10%, right? Because the idea is this area right here, these two areas right here, if I just mirror this, is going to be less than the area of these big blue area here that's shaded in the diagram. Okay. How do I know that? Because that area is 10%. And if I'm beyond that, that means this section here and this section here has to be less than that. And all I need to know whether or not I'm going to reject or fail to reject my hypothesis, my null, is if that p-value is less than that alpha. Okay, so you can't use this method unless you're given a significance level. Okay, so what I am going to do is we are going to reject this. Okay, so my test statistic lies in the rejection region. Okay, so another phrase for that would be rejection region. Okay, and therefore there is enough evidence to support the claim that the percentage of software engineers who rate the company they work for is a great place to work is not 88%. So that is my alternative, right? Is not 88%. I go back up here. Okay. So there is enough evidence to reject that. Okay. So what you say, the values lies in the region. Okay. Forget which one I was reading here. So there is enough evidence. Okay. Yeah. So that's it. So it's in the region. Therefore, the p-value is less than the alpha. So there is enough evidence to support that alternative. Okay. So again, support for the alternative is rejecting the null. Okay. So we'll go ahead and check this real quick here. And sure enough, we're good here. And they got me again for typing in the 0.88 instead of 0.88. But so anyway, that's that. Those are examples of tests for a population proportion. I didn't have, enough time to go through, greater than or less than for the alternative, but they're very, very similar to that. And that's how you go ahead and use this sheet to do this. Okay. As far as this, we could have gone up here to get the 1.645. Actually, looking over here now, I showed you how to use that calculator, the Alex calculator here. Okay, using this command, which was this one here. So if I put in 0.05, just real quick to show you here, that was my 1.645. We could kind of fudge it on this one here using the confidence levels. I don't know if you guys learned that yet. A lot of times we teach confidence intervals before the hypothesis test, but if you do the complement of the 10% here, which would be 90%. So if I change this to 0.90 right here, that means 90% is in the middle, which would mean 5% in the right, 5% in the left. And here's your 1.645 right here. So that would be a way of using this sheet here. And I was trying to look over here on the normal, and I didn't see oh, wait, here would be, I'm sorry. Here, so if the left probability area, so again, if we had 10%, right, and that would mean 5% in the tail. So let's say if I put in 0.05 here, and as long as I use a standard deviation, you know, for the standard normal, which would mean that's 1 and the mean would be 0, that's the Z distribution. Here it is, you know, here's that left one, right? And if I want 95% to be to the left, you know, 0.95. Okay, here's your 1.645. So sorry, yeah, that's in there. We could also use the proportion template to do that. And like I said, I'm not as familiar with this sheet. This is a customized spreadsheet that's made up, and whoever did this did a very nice job, you know, having all this stuff readily available for you. But in the past, I've always used other software, you know, like the graphing calculator and so forth over here instead of using, you know, spreadsheets. And we just did that in high school because you can lug that around with you and always have it available. So, all right, so that's it for these particular ones here. And I will be putting up another video for the test for population means. And I also looked in there, and there's also one for population variance. So, but the nice thing is once you know the basic idea, the structure, the reasoning of these, it's just a matter of, you know, punching in different numbers based on the type of data that you have. And this was categorical data here. You know, we're always getting, you know, here, yes and no for answers. You know, we're not collecting numbers, we're collecting, you know, qualitative data. So, all right. So that's going to be it. I will wrap that up. And again, you will get this, well, you've already found this video if you're looking at it. So, but you'll get another one here dealing with population means and a few more examples here. So, all right. Guys have a great day, and God bless.